The standard story, a universe from nothing. For nearly a century, the Big Bang Theory has been the cornerstone of cosmology. It's taught in schools, featured in documentaries, and generally accepted as the scientific explanation for how the universe began. The story goes like this. 13.8 billion years ago, the universe began. Not just the matter and energy in the universe, but space and time themselves. There was no before, because time itself began at that moment. Asking what came before the Big Bang is like asking what's north of the North Pole. The question is meaningless, because you can't go further north than the northernmost point. At E=0, everything existed as a singularity, an infinitely dense, infinitely hot point containing all the matter and energy that would eventually become the entire universe. Then, for reasons we don't fully understand, this singularity began expanding explosively. In the first fraction of a second, the universe underwent cosmic inflation, expanding faster than light by a factor of at least 10 to the 26th power. This exponential expansion stretched quantum fluctuations to cosmic scales, creating the seeds of all structure we see today. As the universe expanded, it cooled. Within the first second, fundamental particles formed: quarks, electrons, photons. Within the first few minutes, these particles combined to form the first atomic nuclei, hydrogen and helium. Within 380,000 years, atoms formed, and the universe became transparent to light. That ancient light, stretched by expansion into microwave wavelengths, is what we observe today as the cosmic microwave background radiation. Over billions of years, gravity pulled matter together into the first stars, galaxies, and eventually planets. About 9 billion years after the Big Bang, our Sun and Earth formed. About 13.8 billion years after the Big Bang, humans evolved and began asking questions about where it all came from. This narrative is supported by overwhelming evidence. The universe is expanding. Galaxies are moving away from each other in all directions, consistent with space itself expanding. The cosmic microwave background. We can literally see the afterglow of the Big Bang, exactly where and how the theory predicts. The abundance of light elements. The ratio of hydrogen to helium to other light elements matches Big Bang predictions precisely. The age of the oldest stars. The oldest stars we can find are younger than 13.8 billion years, consistent with the universe's age. The Big Bang Theory is not speculation. It's one of the most thoroughly tested and confirmed theories in all of science. But it has a problem. A profound, unsettling problem that has bothered physicists since the theory was first proposed. The singularity problem, where physics breaks. At the heart of the Big Bang Theory is a singularity, a point where the entire universe was compressed to infinite density, infinite temperature, and zero volume. Physicists hate infinities. When infinities appear in equations, it usually means the theory has reached its limit, the point where it can no longer accurately describe reality. At the Big Bang singularity, both of our most fundamental theories, general relativity, which describes gravity and spacetime, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales, give contradictory predictions. General relativity says, as matter becomes infinitely dense, spacetime curvature becomes infinite. The equations break down. They can't tell us what happens at the singularity itself. Quantum mechanics says nothing can be confined to a single point. The Heisenberg uncertainty principle guarantees that particles have fundamental limits on how precisely their position and momentum can be known. A singularity violates this principle. The two theories are incompatible at the Big Bang. Both can't be right about what happened at T=0. This isn't just a technical problem for physicists to sort out. It's a fundamental indication that our understanding is incomplete. The Big Bang Theory can tell us what happened from about 10 to the minus 43 seconds, the Planck time, onward. But it cannot tell us what happened at the very beginning, or why the Big Bang occurred. It's like having a movie that starts a few frames after the opening scene. We can see everything that follows, but the crucial first moment, the moment that explains why the movie exists at all, is missing. For decades, cosmologists lived with this gap, assuming that future theories would eventually fill it. But in recent years, a revolution has begun. multiple independent lines of research are converging on a stunning possibility. The Big Bang wasn't the beginning at all. The bouncing universe, cosmic recycling. One of the oldest alternatives to the beginning from nothing story is the cyclic or bouncing universe model. The idea is simple but profound. What if the Big Bang that created our universe was actually a big bounce, a rebound from a previous universe that had collapsed? The classical oscillating universe. In the 1920s and 30s, even as the Big Bang theory was being developed, some physicists proposed an alternative. Perhaps the universe oscillates, expanding and contracting in endless cycles. Each cycle would last hundreds of billions of years. The universe expands from a Big Bang. Expansion slows due to gravity. Eventually, expansion stops and reverses. The universe contracts in a big crunch. At maximum contraction, conditions become similar to the Big Bang. A bounce occurs, initiating the next cycle. This model had philosophical appeal. It eliminated the problem of a beginning. The universe has always existed and always will exist, endlessly cycling through expansions and contractions. No creation event, no singularity at t equals 0. But there were problems. Entropy increases with each cycle. The second law of thermodynamics says that disorder, entropy, always increases. Each cycle should be more disordered than the last. Eventually, the universe should reach maximum entropy, a state of uniform, boring equilibrium where nothing interesting can happen. But we observe a low-entropy universe full of structure and organization. If cycles had been occurring eternally, we should observe maximum entropy. Current observations show accelerating expansion. Since the late 1990s, we've known the universe's expansion is accelerating, not slowing. Dark energy appears to be pushing the universe to expand faster over time. This makes eventual collapse, and therefore a bounce, seem impossible. These problems seemed fatal to the cyclic model. For decades it was largely abandoned. Then, in the early 2000s, a new generation of physicists revived the idea with modern twists. The ekpyrotic/cyclic model. Physicists Paul Steinhardt at Princeton and Neil Turok at Cambridge proposed a radically updated cyclic model based on string theory and extra dimensions. In their model, our universe is a three-dimensional membrane, floating in higher dimensional space. Not far away, perhaps just millimeters in the extra dimension, is another parallel brane. We can't see or access the other brane because we're confined to our own, like two-dimensional beings trapped on separate sheets of paper. The two branes periodically collide. Every trillion years or so, the branes come together. When they collide, the kinetic energy of collision converts to matter and radiation on both branes. From inside our brain, this collision looks like a Big Bang, an enormous release of energy creating hot, dense conditions from which the universe expands. Between collisions, the universe is nearly empty. After each bang, the universe expands and cools for hundreds of billions of years. Stars form, live and die. Galaxies form and eventually spread apart as expansion accelerates. Eventually, nearly all matter decays or disappears behind cosmic horizons. The universe becomes cold, empty, and dark. But the branes slowly approach each other again. Gravitational attraction or other forces in the higher dimensional space gradually draw the branes back together over trillions of years. Eventually, another collision occurs, another Big Bang, and the cycle repeats. This model elegantly solves several problems. No singularity. The collision isn't a singularity. It's a high-energy event, but not one with infinite density. Physics doesn't break down. It just involves conditions we don't currently understand. Entropy can decrease. During the long periods between collisions, entropy increases and the universe becomes disordered. But during the collision, the brane's kinetic energy creates fresh matter and radiation in a low entropy state, resetting the entropy clock. Accelerating expansion isn't a problem. The current acceleration just means this cycle will last longer before the next collision. It doesn't prevent future bounces. Before the Big Bang, there was a previous cycle, and before that, another cycle. The universe has no beginning, just an endless series of collisions and expansions. Steinhardt and Turok's model makes testable predictions about subtle features in the cosmic microwave background radiation. So far, observations haven't confirmed or ruled out the model. It remains a viable possibility. Loop quantum gravity bounces. An entirely different approach comes from loop quantum gravity, a theory attempting to unite quantum mechanics and general relativity by treating spacetime itself as quantized, made of discrete chunks, rather than continuous. In loop quantum gravity, spacetime is woven from loops and networks at the smallest scales, the Planck scale, about 10 to the negative 35th meters. At this scale, spacetime has structure, like fabric has a weave when viewed under a microscope. When researchers apply loop quantum gravity to cosmology, something remarkable happens. The Big Bang singularity disappears. Instead of density and temperature becoming infinite at t equals 0, they reach a maximum finite value. Very large, but not infinite. Then, following the equations backward in time past this maximum, you find that the universe wasn't shrinking toward a singularity. It was expanding from a previous phase. The Big Bang was actually a big bounce, a transition point where a previously contracting universe reached maximum density and began expanding again. Before our Big Bang, there was a previous universe collapsing under gravity. As it contracted, quantum effects became important at extremely high densities. These quantum effects created a repulsive force, quantum gravity, acting to prevent infinite compression. At a critical density, large but finite, the contraction stopped and reversed. The universe bounced, expanding outward in what we call the Big Bang. Dr. Abhay Ashtekar and his colleagues at Penn State have shown that this bounce is a generic prediction of loop quantum gravity. It's not an added assumption, it emerges naturally from the mathematics. If true, this means time extends infinitely into the past. There was no first moment. The universe has always existed, bouncing through cycles, each bounce resetting conditions for the next expansion phase. The Big Bang was a transition, not a creation event. It marked the change from contraction to expansion in our current cycle, but it wasn't the beginning of everything. Information can survive the bounce. Unlike classical Big Bang models where everything is reset at the singularity, in bounce models, some information from previous cycles might survive. Perhaps the structure we see in our universe, the patterns in the cosmic microwave background, the distribution of galaxies, carries faint imprints of what came before. This possibility is simultaneously mind-bending and scientifically testable. Researchers are looking for specific signatures in cosmological observations that would reveal traces of pre-bounce physics. Eternal inflation, the multiverse origin. While bounce models suggest our universe emerged from a previous cycle, eternal inflation offers a completely different answer to what came before, an eternal, ever-expanding inflationary field that constantly spawns new universes like ours. Understanding cosmic inflation. First, a quick review of inflation. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion, growing faster than light by an enormous factor. This inflation was driven by a hypothetical scalar field called the inflaton field. Inflation solves several problems in standard Big Bang cosmology. The horizon problem: why is the universe so uniform when regions on opposite sides couldn't have been in causal contact? Because they were in contact before inflation, then were stretched apart. The flatness problem: why is space so geometrically flat? Because inflation stretched any curvature to undetectable scales. The structure problem: where did galaxies come from? Quantum fluctuations in the inflaton field were stretched to cosmic scales, providing seeds for structure. Inflation is widely accepted because it explains observations that standard Big Bang theory cannot. The cosmic microwave background's detailed properties match inflation's predictions with remarkable precision. But here's where it gets interesting. Inflation is eternal. In most regions of space, once inflation starts, it never stops. Here's why. The inflaton field that drives inflation is subject to quantum fluctuations. In most regions, these fluctuations cause the field to decay, ending inflation. That's what happened in our universe about 10 to the negative 32nd seconds after our Big Bang. But in some regions, quantum fluctuations boost the field instead of depleting it. In those regions, inflation continues. And here's the key insight, developed by physicists like Alan Guth, MIT, Andre Linde, Stanford, and Alexander Vilenkin, Tufts. The regions where inflation continues expand faster than the regions where it ends. Even though inflation ends in some places, creating universes like ours, the inflating regions between those universes expand so rapidly that the total volume of inflating space keeps increasing. Inflation, once started, never completely stops. It's eternal into the future. This creates a multiverse, a vast, ever-growing cosmic landscape containing infinitely many pocket universes like ours, each one a region where inflation ended and normal expansion began. Our Big Bang was just one local ending of inflation, but inflation itself continues elsewhere, eternally spawning new Big Bangs. Eternal into the past? If inflation is eternal into the future, was it also eternal into the past? Did it have a beginning, or has it been going on forever? This question led to decades of debate. Argument for eternal past. If inflation is self-sustaining, if it naturally continues indefinitely once started, then why would it need a beginning? Perhaps the inflating state is the natural, default state of reality. It's always been there, always will be, spawning universes eternally. Argument against eternal past. In 2003, cosmologists Arvin Borda, Alan Guth, and Alexander Vilenkin published a theorem, the BGV theorem, showing that any universe that has been, on average, expanding must have had a beginning. Even if there are periods of contraction mixed with expansion, as long as the average expansion rate is positive, which it must be if we observe expansion now, you can't trace the universe's history infinitely far into the past. At some point, there must have been a beginning. This seemed to close the door on eternally pre-existing inflation. Inflation must have started sometime, something must have come before it. But the debate didn't end there. What could start inflation? If eternal inflation had a beginning, what came before that beginning? Several proposals exist. Quantum tunneling from nothing. Alexander Vilenkin proposes that the inflating universe tunneled into existence from literally nothing. Not empty space, but the absence of space, time, matter, energy, and even physical law. Quantum mechanics allows particles to tunnel through barriers they classically couldn't cross. Perhaps the universe itself tunneled from non-existence to existence through quantum processes. This sounds absurd. How can something come from nothing? But in quantum field theory, nothing, the quantum vacuum, is actually quite active, full of quantum fluctuations and virtual particles popping in and out of existence. Vilenkin's proposal extends this. Given the right quantum rules, a universe, complete with space, time, and an inflating field in a high-energy state, could quantum tunnel into existence from literally nothing. The probability of this happening is incredibly small, but in quantum mechanics, anything with non-zero probability can happen. Given eternity, or timelessness, as a backdrop, even incredibly improbable events eventually occur. From a previous contracting phase. Even though the BGV theorem says expansion must have had a beginning, it doesn't rule out a bounce. Perhaps before inflation started, the universe was contracting. At some critical point, quantum effects caused a bounce, initiating inflation. This is compatible with both eternal inflation future and a bounce model past. From a pre-existing quantum state. Perhaps the fundamental reality is not space-time but quantum information or quantum fields existing in some timeless, eternal state. Our universe, with its time, space, and inflation, emerged from this quantum substrate as one particular outcome of quantum processes. This view suggests "before the Big Bang" is a misleading phrase because "before" implies time, and time itself is an emergent property that doesn't exist in the fundamental quantum realm. Each of these proposals pushes the question back one step, but none provides a final answer. Even if the universe tunneled from nothing, why do quantum mechanical rules allow such tunneling? Even if quantum states are fundamental, why do those particular states exist? Conformal cyclic cosmology, Penrose's radical idea. One of the most imaginative proposals for what came before comes from Roger Penrose, the Nobel Prize-winning physicist renowned for his work on black holes and general relativity. Penrose's conformal cyclic cosmology, CCC, proposes that the universe goes through infinite cycles, but in a way completely different from bouncing models. The far future universe. To understand CCC, start by thinking about the universe's far future, trillions of years from now. All stars will have burned out. All black holes will have evaporated through Hawking radiation. The only remaining particles will be massless particles, photons, and perhaps gravitons. The universe will be cold, empty, and expanding forever. In this far future state, nothing has mass. And here's where Penrose makes a profound observation. For massless particles, time has no meaning. Photons traveling at light speed experience no passage of time. From a photon's perspective, its emission and absorption happen simultaneously, even if billions of years pass in our reference frame. Similarly, space has no absolute meaning. A photon doesn't experience traveling through space the way massive particles do. In mathematical terms, the far future universe loses its sense of scale. Whether space is large or small becomes meaningless when everything is massless. The mathematical trick. Penrose uses a mathematical transformation called conformal rescaling. This rescaling changes the scale of space-time, making it bigger or smaller, while preserving angles and light rays paths. Here's the magic. Through conformal rescaling, the infinite future of one universe can be mathematically mapped to the Big Bang of the next universe. The far future of our universe, cold, empty, infinite in extent, can be rescaled to look exactly like the hot, dense, tiny beginning of a new universe. From this perspective, our Big Bang was the rescaled infinite future of a previous universe. Our universe's infinite future will become the Big Bang of the next universe. The cycle repeats eternally. There's no bounce, no collision, no quantum tunneling, just a mathematical continuity between the end of one universe, which loses meaning as everything becomes massless, and the beginning of the next. Evidence in the CMB? Penrose claims to have found evidence for CCC in the cosmic microwave background. He and his colleagues report detecting circular patterns in the CMB, concentric rings of slightly higher or lower temperature. These rings, Penrose argues, are the imprints of black hole collisions in the previous universe. When supermassive black holes collided in the previous universe, they emitted gravitational waves. These waves propagated through the universe's entire history into the far future. When that far future became our Big Bang through conformal rescaling, the gravitational waves' influence showed up as circular patterns in the CMB. If true, this would be direct observational evidence of events before the Big Bang, proof that something came before. However, most cosmologists are skeptical. Independent teams have analysed the CMB data and found no convincing evidence of these circles, or argue that similar patterns appear in random simulations, suggesting they're statistical artifacts rather than real signals from a previous universe. The debate continues, but Penrose's model demonstrates how creatively physicists are thinking about pre-Big Bang scenarios. Quantum cosmology, a universe from quantum foam. Perhaps the most radical approaches to before the Big Bang come from quantum cosmology, applying quantum mechanics to the universe as a whole. The Wheeler-DeWitt equation. In the 1960s, John Wheeler and Bryce DeWitt derived an equation describing the quantum state of the entire universe. The Wheeler-DeWitt equation is strange. It has no time variable. Time, which we experience as flowing from past to future, doesn't appear in the fundamental equation describing the universe's quantum state. This suggests something profound. Time might not be fundamental. It might be an emergent property that appears only when you have a large, classical universe, but doesn't exist at the quantum level. If time isn't fundamental, then, before the Big Bang, becomes a nonsensical phrase. There is no before at the quantum level, just timeless quantum states with different properties. The Big Bang, from this perspective, is the moment when time emerges from timeless quantum processes. The Hartle-Hawking no-boundary proposal. Stephen Hawking and James Hartle proposed one solution to the Wheeler-DeWitt equation, the no-boundary proposal. Imagine trying to find the universe's beginning by going backward in time. As you approach the Big Bang, time becomes more and more space-like. It gradually transforms into a spatial dimension. Near the beginning, you have 4 spatial dimensions, and no time dimension. There's no edge or boundary, just smooth, finite, four-dimensional space, like the surface of a sphere has no edge or boundary. As you move away from this region, one spatial dimension gradually becomes time-like, and you get normal space-time with 3 space dimensions and 1 time dimension. The universe has no beginning in time because time doesn't exist before a certain point. Asking what came before is like asking what's south of the South Pole. The question assumes a direction that doesn't exist. Hawking famously wrote, "The boundary condition of the universe is that it has no boundary." The tunneling proposal. An alternative quantum cosmology approach, championed by Alexander Vilenkin and others, is the tunneling from nothing proposal mentioned earlier. The universe begins as a quantum fluctuation, a tiny bubble of space in an excited state, containing the inflaton field that will drive inflation. This bubble has no cause. It appears spontaneously from the quantum vacuum through tunneling. Once created, the bubble immediately begins inflating, growing exponentially and eventually becoming our observable universe. Nothing, in this context, isn't absolute nothingness. It's a quantum mechanical state, a state with no classical space or time, but which obeys quantum rules and can produce something through quantum fluctuations. Critics argue this doesn't truly explain creation from nothing, because quantum rules themselves are something. They're a structure, a framework, a set of laws. Where do those laws come from? Vilenkin's response: perhaps quantum rules are the only logically consistent possibility, and anything logically consistent has a kind of existence. The universe doesn't need a cause, because mathematical logical existence is sufficient. This is philosophically deep territory, blurring the lines between physics, mathematics, and metaphysics. The simulation hypothesis, before the beginning of the simulation. A completely different answer to what came before comes from the simulation hypothesis. Perhaps our universe, including its Big Bang, is a computer simulation created by an advanced civilization in a base reality. From inside a simulation, the Big Bang would appear to be the beginning, the moment when the simulation started. But from outside, in the base reality where the computer exists, there would be time before the simulation started. Before the Big Bang would simply be the time in base reality before someone pressed run on the universe simulation. This idea, popularized by philosopher Nick Bostrom, is taken seriously by some physicists because it's potentially testable. Simulations have computational limits. If our universe is a simulation, we might detect artifacts, glitches, pixelation at small scales, maximum frame rates showing up as speed of light limits, or Planck-scale discreteness showing that spacetime is quantized like pixels. It solves fine-tuning problems. Our universe's physical constants seem precisely tuned for life. Change them slightly, and stars, chemistry, or complexity become impossible. If we're in a simulation, this makes sense. The simulators deliberately set parameters to allow interesting outcomes. It provides a reason for existence. Why does the universe exist? In the simulation hypothesis, because someone created it, perhaps for research, entertainment, or purposes we can't comprehend. However, the simulation hypothesis is controversial. It's unfalsifiable in principle. Any test could be part of the simulation. It pushes the question back. What created the base reality? It's more philosophy than physics. Many physicists view it as untestable speculation. Still, it represents one possible answer. Before our Big Bang was base reality, which might have completely different physics, dimensions, or properties than our simulated universe. The eternal question: why is there something rather than nothing? All these models, bouncing universes, eternal inflation, conformal cycles, quantum creation, address what came before the Big Bang. But they all face a deeper question. Why does anything exist at all? Even if the universe bounces eternally, why does the bouncing occur? Even if quantum rules allow creation from nothing, why do those rules exist? Even if we're in a simulation, why does base reality exist? This is perhaps the fundamental question of metaphysics, and it might not have a scientific answer. Possible responses. 1. Infinite regress. Maybe there's no ultimate answer. Every explanation requires a deeper explanation, forever. Universes come from quantum fields, which come from mathematical structures, which come from logical necessity, which comes from something else, infinitely. Most philosophers find infinite regress unsatisfying, but perhaps reality simply is infinitely deep. 2. Necessary existence. Maybe something exists necessarily. It couldn't possibly not exist. This could be mathematical structures, Tegmark's mathematical universe hypothesis, quantum fields, God or some ultimate reality, abstract logical principles. If something exists necessarily, then the question, why does it exist, is answered, because non-existence is impossible for it. 3. Brute fact. Maybe existence is a brute fact, something that's true without explanation. The universe exists because it just does. No reason, no cause, just is. This seems intellectually unsatisfying, but it might be correct. Perhaps not everything has an explanation. 4. The question is meaningless. Maybe, why is there something rather than nothing, is a malformed question, like, what does blue smell like? It assumes causation and explanation apply to existence itself, but perhaps they don't. Maybe, nothing isn't even a coherent concept. Maybe, something is the only possibility, and nothing is a linguistic concept that doesn't correspond to any real or possible state. The Leibnizian crisis, philosopher Gottfried Leibniz called this the fundamental question of metaphysics. Why is there something rather than nothing? Leibniz believed everything must have a sufficient reason, an explanation for why it is as it is, rather than otherwise. He concluded there must be a necessary being, God, whose existence requires no explanation and from which everything else derives. But modern physics often resists this reasoning. Quantum mechanics is fundamentally probabilistic. Some things happen without cause. Virtual particles appear and disappear without reason. Radioactive decay occurs randomly, with no underlying cause determining when any particular atom decays. Perhaps existence itself is similarly causeless. Perhaps the universe exists as a brute quantum event, something that happened without reason, without cause, simply because quantum rules don't forbid it. What current science actually says? With all these speculative models, what does mainstream science actually say about before the Big Bang? The honest answer: we don't know. Here's what we do know. 1. The Big Bang happened. About 13.8 billion years ago, our universe was in an extremely hot, dense state and has been expanding ever since. This is observational fact, confirmed by multiple independent lines of evidence. 2. We can trace the universe's history back to about 10 to the minus 43 seconds after the Big Bang, the Planck time. Before that, our current theories break down. 3. Something must have set initial conditions. The universe's properties, its expansion rate, matter content, and structural patterns, require explanation. The Big Bang theory describes evolution from those initial conditions, but doesn't explain why those particular conditions existed. 4. General relativity predicts a singularity at t equals 0, where density and temperature become infinite. But physicists believe this prediction is wrong. It signals where our theory fails, not what actually happened. 5. A complete theory of quantum gravity is needed to describe what happened at the very beginning. We don't yet have such a theory, though candidates like string theory and loop quantum gravity are being developed. 6. Several models can potentially explain pre-Big Bang physics, including bouncing/cyclic universes, eternal inflation spawning pocket universes, quantum creation from nothing, conformal cyclic cosmology. 7. These models make testable predictions. Some predict specific patterns in the cosmic microwave background, gravitational waves, or other observables. As our instruments improve, we may be able to rule some models in or out. 8. The question, what came before, might not have meaning if time itself emerged at or near the Big Bang. The scientific consensus is that we're on the frontier of knowledge. We have plausible models but no definitive answers. The next generation of observations, from more sensitive CMB measurements, gravitational wave detectors, and other instruments, will hopefully narrow the possibilities. The philosophical implications. The question of what came before the Big Bang isn't just scientific, it has profound philosophical and existential implications. Does time have a beginning? If the Big Bang was the start of time, then time is finite into the past. There are only a finite number of moments between now and the beginning. The past is bounded. If bouncing or eternal models are correct, time extends infinitely into the past. There is no first moment. Time is unbounded. Which is correct changes our fundamental understanding of causation, explanation, and the nature of reality. Does the universe need a creator? Many religious traditions posit a creator who brought the universe into existence. If the Big Bang was the absolute beginning of everything, including time, then causation breaks down and the concept of a creator becomes challenging. What caused the creator? But if the universe emerged from quantum processes, or bounced from a previous state, or is part of an eternal inflation, then creation becomes less necessary. However, these scientific models don't eliminate theology, they just shift it. A religious believer might say God created the quantum rules allowing universe creation, or set up the conditions for eternal inflation, or exists outside before the multiverse. Science can potentially explain the universe's physical origin, but struggles with why these particular laws? Or why anything at all? Is our universe special? If our Big Bang was the only one, a unique event, then our universe is special, possibly meaningful in some cosmic sense. If Big Bangs happen constantly in eternal inflation, or if universes cycle endlessly, then ours is just one among countless others. We're not special, just one random outcome among infinite possibilities. This affects how we think about meaning, purpose, and our place in reality. Are we alone? If the universe began 13.8 billion years ago, and complex life took billions of years to evolve, we might be among the first civilizations in cosmic history. If the universe is much older, if previous cycles existed, or if we're in one bubble among countless others in eternal inflation, then civilizations might have arisen countless times before, in earlier cycles or other bubble universes. Perhaps some reached incomprehensible levels of advancement. Perhaps they learned to survive universe-ending events, or escape to other universes. Perhaps they're watching us, as ancient civilizations watch our universe's youth. Or perhaps each universe is isolated, each civilization alone in its bubble, unable to contact or even know about the others. The quest for answers. What's next? Science is actively working toward answers. Several upcoming projects might provide crucial data. CMB polarization experiments. The cosmic microwave background contains polarization patterns, tiny alignments in how its light waves oscillate. These patterns encode information about the universe's earliest moments. One particular pattern, called B-mode polarization, would be created by primordial gravitational waves from inflation or a bounce. Detecting this would provide evidence for specific pre-Big Bang scenarios. Multiple experiments, including the Simons Observatory in Chile and the proposed CMBS-4 project, are designed to detect these signatures. Gravitational wave astronomy. Gravitational waves from the universe's earliest moments, perhaps from a bounce or from phase transitions during inflation, might be detectable. Future space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, will be sensitive to frequencies that could reveal primordial gravitational waves. Large Hadron Collider and Future Colliders, the LHC and proposed future particle accelerators might create conditions similar to the early universe, allowing physicists to test theories of quantum gravity and high-energy physics relevant to the Big Bang. While we can't recreate the exact conditions of the Big Bang, we can probe the physics that governed it. Theoretical breakthroughs. Perhaps most importantly, theoretical physicists continue developing quantum gravity theories, especially string theory and loop quantum gravity. A complete, testable theory of quantum gravity would let us calculate what happened at the Big Bang with confidence, potentially revealing what came before. Progress is slow but steady. We're closer now than ever before to answering questions that were pure philosophy a century ago. Living with mystery. As I write this, the question, what came before the Big Bang, remains unanswered. We have models, hypotheses, and mathematical frameworks. We have observations that constrain possibilities. We have brilliant minds working on the problem, but we don't have a definitive answer, and perhaps we never will. Some questions might be fundamentally unanswerable, not because we lack technology or intelligence, but because the questions touch on limits of what can be known from within a universe. If time itself began with the Big Bang, then before is meaningless, and we're asking a question as nonsensical as, what's colder than absolute zero? If we're in one bubble universe among infinite others spawned by eternal inflation, we can never observe those other universes, or the inflating space between them. They're forever beyond our cosmic horizon. If quantum processes created our universe from a timeless quantum state, then asking what came before misunderstands the nature of time itself. Yet this uncertainty, this living on the edge of the knowable, is precisely what makes cosmology so profound. What we've learned, rethinking everything. Even without definitive answers, the search for what came before the Big Bang has fundamentally changed how we think about reality. Time might not be fundamental. For most of human history, time seemed obviously fundamental, an absolute backdrop against which events unfold. Einstein showed time is relative, flowing differently for different observers. But even in relativity, time exists as a dimension. Quantum cosmology suggests time might emerge from more fundamental, timeless quantum states. Time might be like temperature, something that appears at macroscopic scales but doesn't exist at the deepest level. If true, the very framing of before needs revision. The universe doesn't evolve in time. Time is a property of the universe that emerges under certain conditions. This is philosophically revolutionary. It means our intuitive sense of past, present, and future might be an illusion, a useful description of macroscopic reality, but not fundamental truth. Creation might not require a creator. Quantum mechanics allows events without causes. Particles appear and disappear, states change randomly. The universe evolves probabilistically. If the universe itself emerged as a quantum event, tunneling from nothing, or as a fluctuation in eternal inflation, or as a bounce from a previous state, then it doesn't require an external creator or cause. This doesn't disprove God or rule out theological explanations, but it shows that something from nothing isn't logically impossible if quantum rules apply. The universe might be self-causing or uncaused, existing as a brute quantum fact. Religious and atheistic thinkers both grapple with this. Some theologians argue quantum rules themselves require explanation, that God established the laws allowing spontaneous universe creation. Others see quantum creation as eliminating the need for supernatural explanations. The debate continues, but it's now grounded in physics rather than pure philosophy. Our universe might not be alone. Whether through eternal inflation, cyclic bounces, or quantum multiverse branching, most modern cosmological models suggest countless universes exist beyond our own. If true, this is the ultimate Copernican revolution. Copernicus showed Earth isn't the center of the solar system. Later astronomers showed the solar system isn't the center of the galaxy. Hubble showed our galaxy is one among billions. Now cosmology suggests our universe is one among infinitely many. Each step has diminished humanity's cosmic specialness. We're not at the center. We're not unique. We're one tiny part of something incomprehensibly vast. Yet paradoxically, this might increase our significance. In an infinite multiverse, everything that can happen does happen somewhere. Every possibility is realized. Every story is told. Every potential is actualized. In such a reality, our particular universe, with its particular history, its particular physical laws, its particular evolution of life and consciousness, is unique. Infinitely many other universes exist, but none are exactly like ours. We matter not because we're the only ones, but because we're one expression among infinite expressions of what reality can be. The universe is more strange than we imagined. Every answer to what came before reveals a universe stranger than our ancestors imagined. Bouncing universes where our cosmic history is just one breath in an eternal cycle of expansion and contraction. Eternal inflation where big bangs constantly occur, spawning bubble universes throughout an ever-expanding multiverse. Quantum creation where universes appear from literally nothing through quantum tunneling, without cause or reason. Conformal cycles where our universe's infinite future becomes the next universe's big bang through mathematical transformation. Simulated realities where our entire existence is a computation in some higher dimensional computer. Each possibility challenges our intuitions. None would have been conceivable to scientists even a century ago. Who knows what possibilities remain undiscovered? The universe refuses to conform to our expectations. It's weirder, more subtle, more elaborate than we've imagined, and probably weirder than we can imagine given our current frameworks. The personal impact, why this matters. You might be wondering, why should I care about what came before the Big Bang? It happened billions of years ago, or didn't happen at all. It doesn't affect my daily life. But understanding our cosmic origins profoundly affects how we see ourselves and our place in existence. Existential meaning. If the universe has a beginning, if the Big Bang was the start of everything, then existence has a kind of narrative structure. There's a first chapter, a middle we're living through, and eventually an end, whether in heat death, big crunch, or something else. This creates a framework for meaning. We exist within a story with a beginning, and our lives are part of that story's unfolding. If the universe is eternal, bouncing forever, or existing as one bubble among infinite others, then existence has no overarching narrative. It's not a story with beginning and end, but a vast, perhaps infinite exploration of possibilities. This changes how we think about purpose. In an eternal universe, purpose must be constructed locally, in our lives, our relationships, our projects, rather than found in some cosmic plot. Humility and wonder. Grappling with these questions cultivates intellectual humility. The smartest physicists admit they don't know what came before the Big Bang. The most sophisticated theories remain speculative. We're forced to confront the limits of human knowledge. We're clever primates who've learned a lot, but we're still trying to comprehend existence itself, a task that might be beyond our cognitive abilities. This humility is healthy. It reminds us that certainty is rare, that mystery is ubiquitous, and that wonder is an appropriate response to reality. At the same time, it's astonishing that we can ask these questions at all. That brains evolved for survival on African grasslands can contemplate quantum cosmology and probe the universe's origin is miraculous. We should feel wonder at both the universe's strangeness and our ability to partially comprehend it. Connection across time. If cyclic models are correct, if our universe emerged from a previous one, then we're connected to a history far older than 13.8 billion years. Perhaps atoms in your body have cycled through countless universes. Perhaps the patterns in cosmic structure carry information from previous cycles. Perhaps we're part of an unbroken chain extending infinitely into the past. If eternal inflation is correct, we're connected laterally to countless other universes existing right now, beyond our horizon, each with its own history. These connections are abstract. We can't interact with previous cycles or other bubbles, but they change our sense of place. We're not isolated in time and space, but embedded in something vastly larger. The quest for understanding. Perhaps most importantly, wrestling with these questions exemplifies humanity's noblest impulse, the quest to understand. We're the species that looks at the night sky and asks, why? We're not satisfied with immediate experience. We probe deeper, seeking causes, explanations, principles. The question, what came before the Big Bang, sits at the apex of this quest. It's the ultimate why, an attempt to understand the universe's absolute origin, if it has one, or eternal nature, if it doesn't. We might never fully answer it, but the attempt, the development of theories, the collection of data, the refinement of understanding, is itself meaningful. As T.S. Eliot wrote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time." The frontiers of knowledge. As we stand in 2025, the question of what came before the Big Bang remains at the frontier of human knowledge. We have tools our predecessors lacked. Gravitational wave detectors revealing cosmic events, precision measurements of the cosmic microwave background, quantum theories probing reality's foundations, computational power to simulate universes and test theories, international collaboration, pooling knowledge and resources. Within the next few decades, we may have answers, or at least constraints that rule out some possibilities. Imagine if we detect B-mode polarization in the CMB, with patterns indicating a bounce. We'd have evidence of a pre-Big Bang universe. Imagine if we find signatures of bubble universe collisions, confirming eternal inflation. We'd know our universe is one among multitudes. Imagine if quantum gravity theories mature to the point where calculations definitively show what happens at extreme densities. We'd understand whether singularities are real or artifacts of incomplete theories. Imagine if we find correlations in cosmological data that match predictions from previous cycles. We'd have evidence that information survives cosmic resets. Any of these discoveries would be among the most profound in human history, reshaping our understanding of existence as dramatically as Copernicus, Darwin, or Einstein reshaped earlier worldviews. Or we might find that the question is unanswerable, that we're forever limited by cosmic horizons, quantum uncertainty, or the nature of time itself. Even that would be a kind of answer. We'd know the boundaries of possible knowledge. We'd understand that some truths are forever beyond reach from our perspective within this universe. The ultimate questions remain. After exploring bouncing universes, eternal inflation, quantum cosmology, and conformal cycles, we return to where we started. Profound mystery. Did time have a beginning? Or is it eternal, extending infinitely into past and future? Why do quantum laws allow spontaneous creation? And why those particular laws rather than others, or no laws? If the universe bounces, what sustains the bouncing? What is the underlying reality that makes cycles possible? If we're in a simulation, what is base reality, and what explains its existence? Why is there something rather than nothing? This question haunts every model. Even if we explain how the universe emerged from quantum foam, or bounced from a previous state, we haven't explained why quantum foam exists, or why bouncing occurs. These questions might have no answers, at least none expressible in human concepts like causation, time, and reason. Or the answers might be simple but profound, because it must be so. Reality is, existence exists, no further explanation is possible or needed. Or the answers might lie in frameworks we haven't yet conceived, ways of thinking about existence that go beyond our current physics, mathematics, and philosophy. Conclusion. Before the beginning. The question, what came before the Big Bang, started as seemingly simple curiosity. The more we've explored it, the more it's revealed depths beneath depths, mysteries behind mysteries. We've learned that the Big Bang might not have been the beginning, just a transition in something larger and older. We've learned that time itself might not be fundamental. We've learned that creation might not require a creator, and that our universe might be one among infinite others. But we've also learned how much we don't know. The question remains open, with multiple possible answers and no certainty about which is correct. This is both frustrating and exhilarating. Frustrating because we want answers. Exhilarating because we're genuinely on the edge of the knowable, pushing into territory never before explored. Perhaps in 50 years, this article will seem quaint, obviously incomplete, missing crucial insights that future discoveries will reveal. That's how science works. Today's frontier becomes tomorrow's foundation. Or perhaps in 50 years, the question will remain as mysterious as now, having proven resistant to empirical resolution. That too would be a kind of answer, a humbling reminder of limits. Either way, the question, what came before the Big Bang, represents humanity at its best, curious, persistent, willing to challenge assumptions, seeking truth, even when truth is difficult or impossible to reach. We're creatures who look at existence itself and ask, why? That might be our most defining characteristic, more than tool use, language, or culture. We're the question-asking species, and this question, what came before everything, is the deepest question we can ask. It touches on the nature of time, causation, existence, and reality itself. It bridges physics and philosophy, science and theology, mathematics and metaphysics. It reminds us that despite our knowledge, despite our technology, despite our scientific sophistication, we remain fundamentally mystery-surrounded creatures, living in a universe whose origins and ultimate nature we only dimly comprehend. The universe gave birth to beings capable of asking how the universe was born. That recursion, that self-referential loop where the universe contemplates its own origin, is almost unbearably profound. We are, quite literally, the universe trying to understand itself. We're arrangements of atoms and energy that achieved consciousness and turned that consciousness toward the deepest questions imaginable. Before the Big Bang, there was something, or nothing, or quantum foam, or another universe, or timeless mathematical structures, or a previous cycle, or eternal inflation, or God's creative act. or a simulation starting up, or something we haven't yet imagined. We don't know which answer is correct. Perhaps we'll never know with certainty, but we'll keep asking, we'll keep observing, we'll keep theorizing, we'll keep pushing against the boundaries of the knowable, because that's what humans do. We stand at the edge of mystery and reach toward it, knowing we might never grasp it fully, but unable to stop trying. The universe began, or has always existed. Time started, or never started. Something came from nothing, or nothing never was. The question remains, the search continues, the mystery endures. And in that mystery, in that search, in that eternal questioning, we find something deeply, quintessentially human. The refusal to accept that any question is truly unanswerable. The conviction that understanding is possible. The faith that the universe can be comprehended.
We might be wrong about that faith. The universe might be fundamentally beyond our comprehension. The question of what came before might have no answer we can understand. But even if we're wrong, even if the mystery proves eternal, the attempt to understand is worthwhile. The journey matters, even if we never reach the destination. Because in asking, what came before the beginning, we're really asking, what is the nature of reality? Why does existence exist? What does it mean that we find ourselves here, contemplating these questions? These are the most profound questions conscious beings can ask. And asking them, wrestling with them, developing theories, gathering evidence, debating interpretations, is what gives human existence much of its meaning. So we continue asking, we continue exploring, we continue reaching toward the unanswerable, the incomprehensible, the infinite. Before the beginning was mystery. After the beginning is mystery. Between them is this moment, where we stand with our instruments and equations and questions, looking backward toward origins and forward toward endings, trying to comprehend it all. The universe is 13.8 billion years old, or older, or eternal, or newly created, or one cycle in an infinite series, or one bubble in an infinite multiverse. We're still figuring it out, and that's exactly where we should be, at the frontier, pushing forward, knowing that behind every answer lies another question, and that the search for understanding is itself the point. What came before the Big Bang? The honest answer, we don't know yet. The deeper answer, we're working on it, and the search is transforming what it means to be human. The ultimate answer, perhaps the question itself is the answer, that we're the kind of beings who can ask it, who must ask it, who will never stop asking it until we understand, or until we accept that understanding might forever exceed our grasp. The universe began, or it didn't. Either way, the story is more wonderful than we imagined. If this journey through the universe's possible origins and pre-origins left you questioning everything you thought you knew about time, creation, and existence itself, then you're thinking exactly the way scientists at the cutting edge think every day. Subscribe right now, because we're living in an extraordinary era where the biggest questions humans have ever asked are moving from philosophy into science, from speculation into testable theory. Drop a comment below. Do you think time had a beginning, or is the universe eternal? Which model of pre-Big Bang cosmology do you find most compelling? Does it matter for how you understand your own existence? Smash that like button if you want more explorations of the questions that define what it means to be human. The deep, troubling, beautiful questions about why there's something rather than nothing and what it all means. The universe holds its secrets closely, but we're learning to ask better questions. And sometimes, the questions themselves are the most profound answers we'll ever find.